Hello! And today's question is to show that if 2 plus 2 times the square root of 1 plus 12n squared is an integer, then it is a perfect square, or a square number, given that n is in the set of integers, positive or negative. So let's not waste any time and get right into it. Okay, so the first thing I want to do is to let some integer q equal to 2 plus 2 times the square root of 1 plus 12n squared. And q is an integer, so it's in the set of integers. If we want q to be an integer, we want whatever's inside this square root sign to be a square number. So we want 1, let me change my color. So we would want 1 plus 12n squared to be equal to p squared, and we want p to be an integer as well. So with some rearranging, we find that 12n squared is equal to p squared minus 1, and if we split up this 12n squared into 2 times 6n squared equals p squared minus 1, it becomes quite obvious that p squared minus 1 is an even number. If 1 less than p squared is an even number, then p squared has to be an odd number. And that's just quite simple logic there. So p squared must be an odd number. And I'm gonna let p squared equal to 2a plus 1, where a is also an integer. Okay. So we've so far figured out p squared is an odd number, and p squared is equal to 2a plus 1. So if p squared is an odd number, does that mean that p is an odd number? So let's go ahead and try to figure that out. So let's consider a number for 2c. So it's an even number. And c is in the set of integers. So 2c squared is equal to 4c squared, which is also an even number. If we consider one more than 2c, which is an odd number, and we square it, that's equal to 4c squared plus 4c plus 1, which of course is odd. And that tells us that if p squared is odd, that definitely means that p is also odd. And I'm going to let p equal to 2b plus 1 for b in the set of the integers. Okay, so far we've figured out that if p squared is odd, then p is also odd. So let's go ahead and substitute p squared into our expression for q. So q equals 2 plus 2 lots of the square roots of p squared, which is equal to 2 plus 2p. But we know that p is equal to 2b plus 1, so q is equal to 2 plus 2 lots of 2b plus 1. So it's equal to 2 plus 4b plus 2, which is 4b plus 4. But how does that show that q is a perfect square? Well, it doesn't. At least it doesn't show it yet. Let 1 plus 12n squared equal to 2b plus 1 squared. Because 1 plus 12n squared equals p squared, and p equals 2b plus 1, I just let 1 plus 12n squared equal to 2b plus 1 squared. And why I did that was to get some sort of expression for b, or some restriction for b. So let's go ahead and expand this out. So we have 4b squared plus 4b plus 1. The ones cancel out, so we're just going to have 12n squared equals 4b squared plus 4b. Dividing both sides by 4, we're going to get 3n squared equals b squared plus b. Now I'm going to factorize the right hand side, so 3n squared equals b times b plus 1. Alright, cool. So now what I'm gonna do is I'm gonna split up the n. Let's go with light blue. So I'm gonna split it up into alpha and beta. So 3 times alpha squared times beta squared is equal to b times b plus 1. And something to note is that alpha and beta are in the set of integers. Okay, so now we're just gonna equate things here, equate factors. So one possibility is that 3 alpha squared equals b plus 1 and beta squared equals b. Okay, so let's see if this is actually possible. If b is equal to beta squared, then b plus 1 is equal to beta squared plus 1. But then b plus 1 is also equal to 3 alpha squared. So this is telling us that b squared plus 1 is equal to 3 alpha squared. And we already know that a and b are in the set of integers. So this expression here is telling us that an integer, a square number, plus 1 is a multiple of 3. And then what you should wonder now is that even possible? Can a square number plus 1 ever be a multiple of 3? And we have to prove that it can't. And to do that, what this expression here is telling us is that b squared is congruent to 2 mod 3. Because b squared plus 1 is a multiple of 3, b squared itself is 1 less than a multiple of 3, or 2 more than a multiple of 3. So that's why b squared is congruent to 2 mod 3. So let's look at the quadratic residues mod 3 in this color here. So I'm gonna take some integer, square it, and look at the remainder when divided by 3. So we have 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. So our aim is to find a 2 here. If we don't find a 2, then we can conclude that this is not possible, this expression here. So when 1 is divided by 3, remainder is 1. When 4 is divided by 3, it's 1, then 0, and then 1, and then 1, and then 0, then 1, 1, 0, 1. And we see a pattern. And the pattern that we see is 1, 1, 0, 1, 1, 0, 1, 1, 0. And there's never a 2. Because this pattern is going to continue forever, again and again and again. And there's not a 2 here. So that means 1 more than a square number can never be a multiple of 3. So b squared is never congruent to 2 mod 3. Okay, so we can get rid of this possibility here. So that's one possibility out of the way. Now our other possibility is that 3 alpha squared is equal to b, and beta squared is equal to b plus 1. And what this tells us is that 1 more than a multiple of 3 is equal to a square number. And we know that this is definitely possible. If we put 1 instead of alpha squared, we have 3 times 1 plus 1, which is 4. And 4 is equal to 2 squared. So it's a square number, and it works. And you can also use a similar sort of proof that I used earlier to show that the other possibility is not valid, to show that this possibility is valid. And I'll leave that as a task for you guys to do. Okay, so we've got this possibility here. So we know that b plus 1 is equal to beta squared. Okay, so let me go back to this color here. So here we have this expression here. If we factorize a 4 from it, we have 4 times b plus 1. But hang on a second, b plus 1 is equal to beta squared. So we can substitute that into here. So this q is equal to 4 lots of beta squared. And we can simplify that even more. Q is equal to 2 times beta squared. Q is a square number when q is an integer. And that completes our proof. Thank you for watching this video.